Hello, it's Jonathan Broadwell, creator of the Serial Wombat open source project and a consultant at my company, Broadwell Consulting Incorporated, focused on medical device development and embedded systems. If you need help in one of those areas, give us a call. Today we're going to be taking a quick preview of some upcoming stuff that I'm really excited about in the Serial Wombat project around the Serial Wombat 18AB. We're going to be looking at PID Control, which existed before, but in the upcoming version, there's going to be a lot better support for it. This is really the transition of the Serial Wombat 18AB chip from being a smart I/O expander to being a smart I/O expander and real-time control coprocessor. And you'll start to see that branding change coming. So we're going to look at that. We're going to look at the H Bridge control, which is a pin mode that'll be in the next version that I'm really excited about. And we'll be looking at, in addition to the output scaling functions that are available on all proportional outputs that allow a 2D lookup interpolation. And so that's something that is exciting, and I'll show you why here in a minute. So let's take a look at the circuit that we're going to be using as a fun example to show off some of these features. Okay, so this is the circuit that we're going to be using. We've got a Serial Wombat 18AB chip here in the middle. It's got its jumper in place, and we're going to be controlling it from the Wombat panel over UART through a USB to UART converter. This piece right here is something that's really fun for feedback controls, and it's really a perfect demo platform for PID and other types of controls. This is a 10K slider potentiometer that goes through a gear and has a belt that's driven by this brushed motor. The motor takes up to 12 volts, but 5 volts really seems to sling this thing back and forth really fast. So we can either move this guy by hand, or we can have the motor enable and disable, or we can have the motor move the slider back and forth. There's a couple of sets of 10Ks over here. I got this whole thing on AliExpress. I'll put a picture of the ad up if you guys want to play with it. And with the slider potentiometer, it goes from 0 to 10K. And we're going to feed it into pin 0 on the Serial Wombat chip and into ground. We're not using this as a resistor divider. We're going to use the Serial Wombat chip's ability to directly measure resistance. It doesn't perform quite as well as if we do a resistor divider, but I like dusting off some of the pins modes that we don't use as much. We use the analog input quite a bit. Up here we've got a power distribution block. It's designed most directly for servos, but it's good for any time you want a bunch of pins off of power. And it's got these nice tie-ins on the end that go to my USB battery that'll provide power to the motor. As always, I prefer to drive inductive loads off a separate power supply to prevent noise. Pins 18 and 19 are hooked up to this H Bridge chip. Let's talk a little bit about that chip now. So the H Bridge we're looking at is made by Texas Instruments. It's a DRV8833 based chip, and I get them on AliExpress for about 50 cents each plus shipping. And you can see that this is the legged part. It does not have a pad, and so this one is limited to about 500 milliamps per channel, times 2 channels if you want to use them together. We didn't have to do that here. So this is a MOSFET based H Bridge. And what that means essentially is that you don't get an immediate voltage drop. The voltage drop you get is proportional to the amount of current you run through it. And in this case, we see that the on resistance for the high side plus the low side is only 360 milliohms. So if we would run the full 500 milliamps through that, you're still looking at only about 0.15 volts drop, which is much better than some of the BJT based ones that you see where you may get 1.5 volt drop. So, we'll be able to provide 5 volts to our brushed motor through this H Bridge and still get, 4.8 of those, even if we max out the current, which we typically won't. So the important things to know about this particular guy is the limit on this is 10.8 volts, so it can't do 12 volt motors. It is very, very good though at running small motors off of a USB power supply. And it is very, very cheap and very, very compact. So this right now is my current favorite H Bridge motor driver. The other thing I like about this one is it has a fault output. I haven't used that a whole lot, but I have on other professional projects, and it is nice if you want to do diagnostics or if you're allowing the user to connect something up instead of being hardwired, that fault output can be really, really good. Another good thing to note about the MOSFET-based drivers as opposed to the BJT-based ones is that there's also multiple different ways that you can have the current decay with these transistors that are here, depending on whether you set both high or both low. And you can see these kind of, you could see these in the fast and slow decay modes in this diagram. So you can read the data sheet for more on that if that's something that you're interested in. So that's our H Bridge chip, and so the FETs are going to work really, really good for this particular low power motor. We're not going to get almost any losses through our H Bridge, so that should be a really nice choice for that particular application. So, and other than that, we are all set up to go here. So let's open up the Wombat panel and play with this guy a little bit. Okay, I'm going to launch the Serial Wombat panel, and for those of you who are watching this in February of 2024, this introduces some features that are not yet released that I would expect will probably be out in March or April. So I'm going to hook up to the COM port that corresponds to that Serial Wombat chip and USB converter. We'll wait a second for it to initialize. And okay, and it comes up and I'm showing firmware version 9.1.2. That's how I indicate an in development version. This will become 2.1.2 when I release it. So 2.1.2 will be the feature set you'll want to be able to do all this stuff. So let's start with the input. We will go to pin 0 and we will set that up as a resistance input. And we'll just use all the default configurations and say auto sample, and we can see right now it's at about 7K. If I take and slide this guy back and forth, he goes all the way down to almost 0 and up to very close to 10K. So this pot looks like it very much produces what it's marked as, and the Serial Wombat chip is doing a good job measuring it. So let's put this guy over to the side for right now, and we'll look at him some more in a little bit. So we're going to go to pin 18 and introduce the new H Bridge, and this is still in development, so some of these buttons may look a little bit different in the final version, but you get the general idea. Again, we're just going to configure this, and with the H Bridge, the concept of the Serial Wombat chip is that full range goes from 0 to 65,535. If you're talking about something that only goes in one direction, that pretty much means 0 is stop. But for an H bridge that can travel in either direction, then 32,768 is in the middle. That's a stop. So let's come over here and we will turn on our battery. And then let's power this guy one way. Up, he goes all the way that way. Let's power him the other way. That's good. So let's see if we could put him in the middle. And what we see is that there's a pretty big deadband here. In fact, all I get is humming up until I get this thing down maybe below 15,000 and up above about 50,000. So we've got a deadband in there. And so the interesting thing on that is now we have a new output capability, and this is the 2D lookup capability. And as we go through here, we see you can create up to 16 points. And by default, they just come in a line. You could hit configure and send that down to the chip. But what I want is we are going to scale this guy. I know that from prior experience, actually 5 volts moves this a little faster than what I want. So we're not going to let it go all the way to 0. If the input value is 0, we're going to output 2,000. And then we will go up to 30,000 as an input, and we will make that 15,000 output. Now, at 30,001, we're going to do to 32,768. At 30, what's 32,000 plus 3,000? 35,000. 32,768. 35,001. We're going to have that guy be at 50,000. That's 15,000 below 65,000. And then the last point in this interpolation table always has to be 65,535 for the X. And we will have it output 65,535 would be the maximum output, but we said we don't want it to quite travel at maximum speed based on my prior experience tuning this. So I'm going to set this one to 63,500, and something's a little off here. Why is this 1 point going back? 1, 2. Oh, it's because I put an extra 0 in there. There we go. Okay, so we can see this is the output response. If we get an input command that looks like this, then up to a point we're going to scale along this line. We made ourselves a little dead zone in the middle where instead of just making the motor buzz, it's going to turn totally off. Then we get scaling towards the other direction that way. So let's go ahead and enable that and configure that. And we can see, I don't know if you can hear that on the video or not, but inside this entire deadband, we get no power. And so now as I go this other way, what we'll find is that I can get a much smoother transition of power than what I could before, because the lead-in on these slopes is much better. This will help the PID controller work better. Okay, so now let's do the fun part. We're going to disable this because we're not going to run off of pin 18 anymore. We want the PID controller to draw its input from pin 0, which is the potentiometer. And we're going to go over here to feedback control. And actually, this PID is an old one. This is the one we want. This will all be cleaned up later. Like I said, this is a work in progress. The sample period for our PID, I'm going to set up to 8 milliseconds because I know we don't, because of the nature of the resistance input, it uses what's called the charge time management unit on the PIC 256GA702. And so I don't get a new measurement every 1 millisecond, which means it would be dumb to run the control loop at that speed. So let's go ahead and do that. We're going to set, the way that this works, KP is divided by, is in units, they're fractions. The Serial Wombat chip doesn't use floats, it uses fractions. So these are in 256ths. So let's set this one to 256, which is equivalent a KP of 1. And if you don't know what KP, KI, KD are, go out and watch a couple of videos on PID control. That's proportional integral derivative control. It's a really good feedback control algorithm. I'm not going to go into exactly how it works here, but we will look a little bit at how to tune it. So I'm going to come back here. I'm going to say enable. I'm going to turn on output scaling and reconfigure that. Since I turned this off and on, it cleared the whatchamacallit. And then I'm going to go to configure PID. And nothing's happening right now because I think my battery turned off again. And we can hear it humming, and it's just barely trying to move. And okay, so what is it doing? That means that our P is not fast enough, is not large enough to cause a proportional response that will eliminate error. Now, this is what I'm really proud of. Let's look at this show graphs. Wow, okay, all of a sudden there's a bunch of PID stuff here. And we'll put our 256 in there that we had before. And let's say auto update. And we get 3 graphs that are going to help you tune your PID controller. This top one is the error, or what's going on. The error is the difference between the target and the actual input. And we can see this here as well. This is the input. We're setting up about 10,000, and our target right now is 0. We want to drive the thing to 0. And this middle graph is effort. The blue represents the total effort being exerted. And so I want to do one more thing before we go farther. I said before that our goal is always to have 0 to 65,535 be full scale. We know that we get 0 to 10,000 on the input from the potentiometer. So let's tell the Serial Wombat chip to take and scale that up to 0 to 65,535. Now at this point, if I move this back and forth, instead of a 0 to 10,000 rating, we get a 0 to 65,535. That works better for us conceptually, and it'll also actually make the PID controller work better because it'll have more resolution to work with. We don't actually get better points, but because the PID tends to play in between points, it works better. So anyway, what we can see right here is we've got an error that's not getting closed. So let's increase KP. That's a standard thing to do right off the bat. And so we're going to reconfigure the PID controller. And we can see what happened there. Okay, it is... Where did we end up? We went all the way to 0, which is pretty good. Or we got close to 0 anyway. Our target is... We're reading about 2,500, and we were shooting for 0. So that's pretty good. Part of that may be an issue with the scaling that we did. We're going to stay away from the very edges. We're going to play more in the middle here in a minute. So let's put our PID target to halfway up, 32,000. And we have two ways we can update the target. One is to just update it. The other one is to clear the integrator. And which method you want to do for changing targets depends on the nature of your system. In our case, there's not really anything that accumulates that's working against us. An example of that might be trying to drive uphill. It might be a heating system that's automatically losing heat all the time to the air. It could be, wind resistance that you're overcoming, something like that. This particular system doesn't have anything like that. Once we reach the spot, we really don't have to do any work to stay on that spot. So we're going to clear the integrator when we go. And so what happened? Okay, we were shooting for 32,588, and it got pretty good, actually. It came out pretty close. That may have been just a lucky hit. Let's go down to 14,000. Okay, and what do we see now? We see we're oscillating. And what that means is that our KP is too big. If we look here, we can see that that it was chasing it back and forth. And my colors actually changed here from when I made this label. I'll have to go back and explicitly set this. But we can see that we were getting oscillations in our effort. So I'm going to reduce that KP. And we'll go down to 2150 and redo it. And this is an iterative process. And there's controls engineers out there that would be a lot better at this stuff than I am. Feedback control is not my primary focus. So that did a little better. We got a little more oscillation. And how are we doing on our total error? We were shooting for 44,400 and we got 44,300. So let's add a little bit of integrator here. And what we'll see is that the integrator will kick in and is actually pushing us back. This blue line is our target. This is the actual input. We can see that it's actually moving back and forth across that input. So that's really, really good. And so I'm going to go, I tuned this once before. I'm going to just put in the answers that I got through a fair amount of playing that gave me a response that I was really happy with. And 500. Okay. So I'm going to reconfigure the PID and we'll set it down. What my goal was kind of to be able to go from 5,000 to 60,000 without getting too much overshoot. So configure PID. And we can see we went down here. We overshot, but not terribly. And then we can see, if you look at here, the integrator is becoming the major part of the green line is the integrator effort. The blue line is the total effort. And we can see that it is doing a good job pulling that error in. We are right on the target line. So that's really, really good. So let's set this new target up to 60,000 and tell it to move it. And we can see that we did the same thing. We went, it put it right on the dot. And now the integrator is coming in and reducing the last of that little bit of error that we had. But this particular response is really, really good. I like that for this particular thing. And again, we could make it better by using a voltage input rather than the resistance input. That would let us increase the sample period because we're getting real samples more often so that we could control the thing even more precisely and cut that overshoot. Maybe use a little stronger derivative or things like that. So let's put it down to the middle. And we actually got a little bit of oscillation there, but not terrible. And the other thing about the pot is that it's a little bit noisy, that you don't get a real nice, super even smooth. And we've got a derivative term in here. The derivative tends to be really sensitive to noise. So, you know, all of these things, none of this is being apologetic. This is just the nature of the physical system that we have and of the nature of PID control. There's other more sophisticated algorithms, but PID is really, if I could only have one algorithm in the world, PID control would probably be it. And you're going to see that in future videos because we're going to have an awful lot of interesting PID and other related control systems videos. So anyway, I'm really excited about this. If you have an application or you have a feature request related to real-time feedback controller, the PID controller, if you're a controls expert and you're looking at this and saying, boy, you know, if I were you, I'd do it a little bit different, then please leave me a comment down below. You know, I would love to integrate your guys' desires before I release it rather than after I release it, because then sometimes I got to work to try to maintain backwards compatibility. So, but anyway, this is kind of where we're going in the future. I will show you one other thing that is pretty exciting. So one of the other things I'm really excited about, all of this functionality is really neat. People are going to want to use this in Arduino, in Python under Raspberry Pi or MicroPython. And you can do all this through the interfaces that are available for the Arduino C++ or Python libraries. But it's a lot of parameters to cut and paste once you've tuned it. I absolutely would tune my system using the Wombat panel, and we'll sneak peek later a way that you can actually plug in the Wombat panel while you're in circuit talking over I2C. But I would generate my code here. But so I would do my tuning here because you have access to all of these graphs. We saw how we could see, okay, we're getting overshoot or not, you know, closing time, all of that kind of thing. It's very capable. But then you got to actually go into the API and look up the function names and copy these parameters that you picked into your initialization. And this is where this is really powerful. So we're going to hit the Gen PID code button. And then if we go into Arduino and hit paste, this is what we need in order to do the initialization. This is the right set of parameters. This is our KP, our KI, our target value, the period, everything that we did ready to go as code. So that's really pretty handy. And the other major thing that we did here was on this output scaling, we did this 2D lookup. Well, for that, you have to load all of these points and also put the thing into that mode. So that doesn't work yet, but it will. And when it does, it will actually create code that will load all of these parameters into the user buffer and point the output scaling at the user buffer. Then finally, you'll want to generate enable code that goes here. And as you can see, it didn't clear the clipboard. It kept the prior settings. So it's designed so that once you configure your system, you can go through and click all those, load all that code up, and it will automatically create commented, properly parameterized code. So this is still a work in progress. It'll be ready by the time of the next release, but you can see where we're going with this. I'm really, really excited about it because this is going to be a great way for you to create and tune a real-time system and then automatically generate code that you can dump into your Arduino to make it do its thing. So anyway, if you have any comments on this, if you're a controls person, if you have an anticipated use for this, let me know about it because I'd love to be able to address any needs or concerns you have before I release this. That's better for you, and it means that I don't necessarily paint myself into a corner that I didn't see coming. So anyway, very excited about all of this stuff that's going on. I've been spending a lot of my winter at home time working on this stuff. Had a lot of free time on the weekends over January and early February. So really doing a lot with this and excited to be able to get it moving and get it into the hands of you guys. So that's all I have for today. Have fun, keep making stuff. Leave me some comments below with what you think. And check me out on Instagram. You'll also see some updates that are coming through there. So until we meet again, have fun. The Serial Wombat firmware is available on GitHub and is constantly being updated. Subscribe below so that you can see the latest features and videos that come out as we fix bugs and add new features. The Serial Wombat open source project was created by Broadwell Consulting Incorporated. Broadwell Consulting Incorporated provides help developing medical devices with a focus on developing embedded firmware, which is compliant with IEC 62304, ISO 14971, and ISO 13485. As well as remediation assistance for products already in production. For more information, contact John at Broadwell Consulting. Support requests for Serial Wombat should be sent to help@serialwombat.com and will be answered on an as-available basis. Also, feel free to leave your question in the comments below.